Welcome to week 4, I think, of the NC Engine stream. So let's address the elephant in the room. I actually like my new glasses, which is amazing. Maybe we'll jump over to just chatting for now because we have some stuff to catch up on. So I got new glasses, and I've always hated and been really embarrassed by my glasses because I'm incredibly nearsighted. I've got I don't know glasses speak because I always wear contacts because of aforementioned not liking how they make my eyes look, but I have a 5.25 in one eye and then a 4.75 in the other one. So normally when I wear glasses, it makes my eyes look like like pebbles, which is fine, but I'm insecure about it. And I finally found the solution, which isn't a happy one. Well, it kind of is. I went to the eye doctor, and she told me that I have to wear contacts and glasses now. And so here I am. So apparently what's happening is, because I look at screens probably 15 or 16 hours of the day, maybe 14 or 15 hours of the day, my retina is weakening. And because I have astigmatisms in my eyes, apparently the edges of my retinas are weakening, and I need to get something called eye zen, but I think that's just a fancy and expensive name for blue light filtering. So I have to wear these even when I wear my contacts now, but I like them. So happy news. I also got a pair of glasses for when I don't need to wear my contacts or don't want to wear them, but we have a 2-year-old, and generally I try to avoid wearing glasses around said 2-year-old because he likes to take them off my head and put them on his, and they get dropped and they get scratched. I last had a pair of glasses 2 years ago, and they're scratched, but they're scratched exactly where my pupils would be. So it's like looking through a glass darkly when I try to see anything out of them. But that's update number 1. Now, we have a lot of updates today. So when we last left it, I was stuck on my D3D12. Everything was looking absolutely bunk. And to be more precise, I can pull up the scene here. So we were backing up a little bit for those that are new. My husband and I have built a C++ game engine. We started in 2019 or late 2018, somewhere like that. And he just started it as a hobby project because he wanted to learn C++. And I think I joined in maybe late 2019 and didn't know anything about graphics programming at the time. And didn't know anything about C++ except for what I had done in college, which would have been 7-8 years ago before we started. But decided to jump on board because we were both really frosted at Unity. Because I think that was the time Unity was deprecating its networking library that we were actively building a game in, and that was just the last straw for us. So we left using Unity and started investing most of our spare time into this game engine. And I had the idea, so he had started writing it in D3D11, and I had the idea, well, if we're going to learn a game engine, or if I'm going to learn a graphics API, I might as well learn something new. So I started digging into Vulkan, which was a monumental task because I didn't know anything about graphics programming. But one of my favorite things about myself, and it's not as putting myself down as it sounds, but I may not be the smartest developer in the room, although I'm pretty smart, I feel, but I'm the most stubborn, and that gets me through a lot. So I bullheadedly bashed my head against Vulkan for 4 years, and we got to the place where we had a pretty good engine. We were able to make a game with it. We made the Pirate Software Game Jam for 2022, January of 2022, or 2023, January of 2020. Oh my gosh, no, it was this year. This January, we were in the Pirate Software Game Jam, and we're able to make a game with our engine in 2 weeks. And at the time we had we didn't have image-based lighting, but we had a pretty decent PBR renderer, sans image-based lighting, and a toon renderer for this pretty cool toon shader we were building. But because I had started learning Vulkan and developing Vulkan at the same time, every one of my assumptions that had proven to be incorrect at the time, I had to build around rather than undoing. So I had completely violated the principles of, what is it? Is it Yagni? You aren't gonna need it. I decided when I was building the Vulkan renderer that I'm gonna make it as generic as possible and as flexible as possible, which is fantastic, except the thing about you aren't gonna need it is not only do I not need any of the flexibility that I built into the engine that I took, or the graphics renderer that I spent so much time building, but the amount of spaghetti I had to introduce in order to make it generic for use cases that I didn't know we would ever need because I'd never built a graphics renderer, and surprise, surprise, we didn't end up needing them, left us in a state where adding new features to the Vulkan renderer was just impossibly slow for a 2-person nights and weekends team. So I had just started trying to make my dream shader, and that came about from what's the game? I don't remember the game because I've never played it, but someone made a Mobius style shader, which is all the rage now, but a year or two ago I looked into that and I thought, oh, I need to make that. But in order to do that, I needed both a normal pass and I needed, we needed a normal pass and we needed a depth pass, and just the basic idea of being able to produce a render target from a render graph that acts as a shader resource to be input back into the render graph. We had only done that for shadow mapping, but I had done it so specifically for shadow mapping that it was impossible to extend. And if I had done it, and I said so specifically for shadow mapping, but the real catch is the violating of the Yagni, the absolute abuse of the Yagni, because when I was building the render target workflow for shadow mapping, I thought I was making a general, but I didn't know what a second render target would look like if it wasn't a depth pass or wasn't a depth buffer. So I built all of this functionality to try to make it generic, and then it wasn't usable for anything but shadow mapping. But because I had all of that architecture in there, I'd gotten to the point where we just couldn't extend the graphics library anymore. So fast forward to 3 months ago, maybe, we really wanted to start working on a game, and Cal, my other half, he had built his own physics system in C++, which is such a dang accomplishment. I would come downstairs and he'd be reading papers published in obscure research journals and all sorts of crazy articles, and he had used all of that information to write his own physics system, and it was really, really cool. But we couldn't do some things with it that he wanted to do. I couldn't actually tell you what, beyond wheel physics, what limitations his physics engine had, but he had decided that he should probably rewrite it if we're having the conversation of potentially rewriting graphics, which is where we ended up. So at that point we thought, okay, if we're going to talk about rewriting our graphics layer and rewriting our physics layer, let's just pick up Unreal or pick up Unity again and see, maybe that's the fastest way to make a game. And that was a tough decision because the engine now has a life of its own. It's really important to both of us. But we haven't made a single penny from any of these pursuits in the last 5 years because it's open source and we're very under the radar, and we were never building an engine for other people to consume. We were always building an engine with the intention of having a tool for ourselves to make games faster. But because we're a nights and weekends with a 2-year-old team, our time is so limited. if we want to actually start making some kind of supplementary income from this, we had to be serious about, let's pick up other tools. So we demoed Unreal for a couple of weeks, and we found Unreal is amazing. It's incredibly powerful. It's super easy to use. It's beautiful. But we were running into some bugs and problems, and it kind of it gave us flashbacks to the Unity days. And it reminded us of the thing that we don't like about commercial game engines, and the thing that we love so much about having invested the time into our own engine. And that is that if we have a bug, we know exactly where it is. We know we can fix it. We don't have to wait. We don't have to file an issue and wait 6 weeks to 6 years or some nebulous time for a developer to fix it. We can just fix it. And that kind of flexibility, as well as knowing the entire process from beginning to end and every character of our engine, is really cool. And we didn't want to throw that time investment away. So after trying out Unreal, we decided just to jump into option B. And option B was, okay, what if we pull in an open source physics engine and an open source graphics abstraction layer and go from there? And that's what we ended up doing. So Cal pulled in Jolt, which is phenomenal. Jolt is let me see, I'll pull it up. Put it in chat. For those unfamiliar, I know it's a pretty popular library, but for those unfamiliar, I'm going to throw it in chat if I can figure out how to do that. Can she figure it out? Yes, I can. So that is Jolt, and that's the library we decided to pull in for physics, and so far so good. It took Cal like 2 weeks. I think it was a little bit longer than that, but it felt like 2 weeks for him to completely cut over our physics engine to Jolt. And then for graphics, I looked at a couple different options, and we landed on the Diligent engine, which is also very, very cool. And I'll send a link there too. So Diligent engine is really a neat idea. Essentially, so Vulkan is a very, very verbose API, as is I think D3D12, although I haven't spent much time with it, more now than ever. And what Diligent does is it gives you a both platform and API agnostic interface to render using D3D11, OpenGL, WebGL, Vulkan, Metal, WebGPU, Direct3D, D3D12, D3D11, if I didn't say that. So you get a common interface to be able to interact with all these APIs. And when I looked at that, I thought, oh my gosh, that's exactly what we need, because along with our Vulkan render being kind of spaghetti, as much as beloved spaghetti, I'll call it that, beloved spaghetti and really hard to maintain, it was also very fragile. And we didn't have any kind of fallback option. So if you didn't have one of the features that we were using, sorry, we're just going to crash. And I still don't have a good way to proactively detect what drivers support which features. There's Sasha Williams' GPU info, but I can't extract a device set from that. And I've looked into it a little bit. I know that there are the concept of Vulkan profiles, so you can see kind of feature bags that apply to driver bags, and I'll spend a little bit of time later on and figure that out exactly when it does come time to release our game. But so our engine didn't do any kind of fallback cases, didn't do any kind of fallback APIs. We were just straight Vulkan, and if you didn't support our features, or if we surpassed the memory or hardware requirements on your device, we were just gonna crash. And we unfortunately encountered that with one user that tried our game in the game jam. So that was a bummer. And the thing that Diligent offers is, because it's API agnostic and platform agnostic, you have just infinite flexibility. So you can say, okay, we tried Vulkan, this feature isn't present on the device, so let's fall back to either just not using the feature, or we can fall back to D3D11 if you're on Windows, or we can fall back to OpenGL. So that's where we started a couple months ago. And slowly, as we've been trying to add features and get feature parity with what we had before, we've whittled away all of the other APIs. We just got rid of D3D12 in this last week. And so now we just have Vulkan again. But it's still worthwhile to use Diligent because Vulkan's incredibly verbose and he has phenomenal wrappers around just all of the things that would take you 300 to 500 lines of code you can do in just a couple. And we did a really bare bones performance test, as close as we could get with our benchmarking scene. And I found and it wasn't exactly a fair comparison, because even though I stripped out all of the binding of lights and animation and all the things we had before, so we weren't writing to those buffers, and I stripped it down to the very bones, but still there's a lot of variables that we couldn't completely eliminate. But that being said, we were able to render just no culling, no anything in place, just straight up draw calls. We were able to render 120,000 cubes on this computer, which is a GeForce 1070 GTX. We were able to render 120,000 cubes with Diligent, and something like 65 or 70 with our previous implementation. And that's with absolutely no culling, just straight up, here's a giant buffer of data. Now iterate through every one of our transforms and render it. So that gave me a lot of hope. And Diligent also offers a really nice interface to be able to detect features and feature support. That flexibility would have taken quite a long time to write. So that catches us up all the way to this week, I think. So now what I was working on trying to get our object subsystem going. I think that was the last 2 or 3 streams. And I got, let's see, I'll do broad strokes first. So last couple streams I was working on the object subsystem, and all of that does is it's just the front end interface to get from our ECS, the transforms for every renderer object into a buffer on the GPU so that we can get their model matrices. And I was stuck last week because in D3D12, what we were seeing was, here's our scene. We've got a worm made out of cubes. It looks very strange right now because we just have the base color implemented now. And we chose gray for a lot of the base colors. But if you'll see here, I'm clicking on the ground. This is Vulkan now. But what we were seeing in D3D12 last week that I was so stumped on was every object in the scene was being applied by its model matrix. No, it wasn't. So every object in the scene was not being applied by its model matrix. It was just perfectly set right in the middle of the screen. And when I first looked at it, I thought, okay, it looks like we're just not multiplying the vertices by the model matrix, because the instant we do that, they're now in world space, and they were all in local space around 0, 0, 0, or they were in world space around 0, 0, 0. But I spent a good 2 hours on stream last week trying to figure it out, because I ignored my first hunch. Because when I thought, okay, we're not applying the model matrices, I went into RenderDoc and I saw that, oh, and here's the catch. In Vulkan, it looked just like this. We were applying the model matrices to each vertex. But in D3D12, we weren't. So my initial thought was, well, there's something goofy with the buffer. But I looked in RenderDoc, and the model matrices buffer looked different in D3D12 and Vulkan. But all of the data was there. And what I should have done is stop right there and say, wait a minute, if the data was there and we were accessing it correctly, we would not see, or even if we were accessing it incorrectly, we would not see everything centered around 0, 0, 0. So if the data was there and the data was in the incorrect format, we would still see objects scattered all over the place. They wouldn't be centered around the origin. But I have this bad habit of second guessing myself. And I'm going to write on a post-it note and stick it to my monitor that your first hunch is usually right. Don't second guess yourself. You're not crazy. I'm going to put that on a post-it note and follow it, because I went down a rabbit hole for 2 hours on stream trying to figure out, is it a handedness thing? Is Vulkan a different handedness than DirectX? Is it a row major, column major thing? And I could not find the problem. Well, we found the problem sometime last week off stream. The problem, so it was so funny. After doing a deep dive into handedness in column and row major orders and the different APIs, and for like a day, I came downstairs the next morning and I told my husband, I said, okay, I found it. And he said, I found it at the same time. And we both came to the same solution by different means. But the problem was that in our draw call, which has just been moved, let me find out where it went. Okay, so we were still supporting Vulkan and D3D12 at the time. And we have always, excuse me, we have always passed in our draw call the instance index. That's what we did in Vulkan, and that's what we were doing here. So what our typical pattern is, because we use bind list rendering, is we bind the entire object data buffer, which just contains the material or the model matrices. We bind the entire buffer of 100,000 model matrices in order to the GPU once per frame. And then what we do is, for our draw calls, we have a link between the model matrix and the entity ID. And we just say for each entity that has a model matrix and is associated with this pipeline, just increment the index by 1, and that's the index into the model matrix array. And so the bug was so simple, but in Direct3D, if you call, or at least in the diligent implementation of D3D12, if you call draw indexed, but your instance count here is 1 or 0, I don't know why you'd ever do it with 0, but if it's not greater than 1, then he does not propagate the first instance number. And that's probably perfectly reasonable, except that we were relying on the instance to be passed. So in D3D12, so we're using HLSL, because another cool thing about Diligent is you can write your shaders in HLSL, and he will compile it either to SPIR-V or whatever you need for whatever backend you're using automatically. Very, very cool. But so in D3D12 in HLSL, this SV instance ID was getting optimized out because it wasn't set on the CPU side. So this instance ID was always 0. So we were always getting the model matrix for the first object in the model matrix array. And that was it. So you would think, oh, that's a super simple fix. Just pass like a push constant is what I would have done in Vulkan, but unfortunately Diligent doesn't implement push constants yet. So then we thought, okay, well that kind of sucks. We just need a single integer to be passed across the pipe, but we need it now for every single instance. So 100,000 cubes, we've got to map an integer 100,000 times. And without push constant, that does become a bummer, because we can use like a typical uniform buffer, but that gets away from bindless rendering, and it seems like a weird hill to die on, but it was a big enough hill for us to just decide to drop support for D3, D12. So here we are. So let's see, what else was I going to talk about today before we get into the coding? Oh yeah, we have 57 stars on GitHub, and that is really exciting. Whoever watches this, I want you to know that every star that we get, we tell each other about. It's a big deal for us. It's really exciting to see them going up, up, up. Oh, and then my future watchers will never know the struggle, but previously I was using the MSVC generator in CMake, so my build was taking forever. And even if I just had to do something simple like update a config file, it would take 5 to 6 minutes to finish like the checking each file to see if they needed to be updated or rebuilt, even though they didn't, and then doing an install for everything, even if it had to do this up-to-date check. So I switched over to Ninja as my generator, and things are much faster now. So that brings us up to speed. You guys got a history lesson on the engine. And briefly, future goals for us, we are trying to get feature parity as quickly as possible with graphics. Now, I think we're going to be there in just a couple of weeks, maybe now, which is much faster than I initially thought. If you're going to marry someone that's really, really good and really, really devoted to making your dreams come true. That's all I've got to say, because my husband is so good at C++. It's like he eats, sleeps, and breathes it. He's obsessed with getting better, and he's really carried me very far on his shoulders. But he's never been the graphics guy. I was the graphics gal, and I tasked him with helping me cut over to Diligent, and he made a material system in just a matter of a week or two. It's just stuff like that. It's really nice. So now we're going to try to get feature parity as quickly as we can with what we had before, so we can jump right into a game. But one thing that I want to add that we never had before was culling beyond basic frustum culling. And I'm going to attempt to do clustered forward rendering. So we're a forward renderer. I got kind of with the going back to the Yagni and the you aren't going to need it approach. I looked into deferred rendering, but as I was looking into it, I saw a bunch of things now saying that now that the bottleneck isn't so much compute speed, the bottleneck is VRAM. So if you're going the deferred renderer approach, you're going to be bottlenecked by something that is not improving as fast as compute speed. And that made a lot of sense. So deferred rendering requires a lot of screen width texture parameter, or texture screen width screen size textures in VRAM. And I thought, okay, if I'm going to invest some more time into implementing a second renderer, let's do something that's more future proof. And so I found the original guy that came up with clustered forward shading has a bunch of talks about it and a couple papers on it. And I think it's within the realm of possibility to get something like that going. So the rough roadmap for us, or at least for me, is get lights implemented, and that's what I'm going to be working on this stream and probably the next, probably not the next after. I'll probably have it in by then. But I'll be working on just getting the basic point light, directional light, and spotlight triad in. Then as soon as those are in, I'm going to cut away from lights for a while and jump over to culling and spend a couple weeks just trying to make it as efficient as possible. Then I'm going to jump back to lights and get shadow mapping rolling. And then once I'm done with shadow mapping, I'm going to jump over to finally what we've all been waiting for, getting my shader where I want it to be. I am so excited for this shader. I expect probably by mid-December, maybe early January, I'll be to the point where I can work on the shader. And then my streams are going to change quite a bit because I'm actually the art member of the squad. So I'm a programmer by trade and I enjoy it, but what really gets me excited is game art. And I have an idea for a game that I'm pretty excited about. So once we get feature parity and beyond here, we're going to jump into making a game. And that'll probably be a couple months from now. Optimistically, a couple months from now. All right. So I will be right back and use the restroom, and then we will jump into some lighting. Okay. So previously for the object subsystem, I started subsystem first and then went and did the GPU side. But this time for lighting, I've already done the GPU side, minus the shaders, but we've created the buffers, did a really nice little abstraction of the structured buffer type, which I always knew as storage buffer because I'm coming from Vulkan Land, but we made a structured buffer base class and then a structured buffer class that handles all the allocations and updating for you and the resource transitioning. So now we can just quickly use it in a resource signature. And a resource signature is like a descriptor set layout for those coming from Vulkan. It's probably called a resource description or a resource signature in D3D12 land. But I think a resource signature is a slightly broader concept. It spans multiple descriptor sets. So a pipeline can have one or more resource signatures bound to it. And a resource signature can have I'm not exactly sure how Diligent divvies up the descriptor sets within the resource signature. I really need to figure that out because I was always operating under a no more than 4 bound to the pipeline at any given time rule of thumb. And it looks like we're pretty fast and loose with resource signature, or with bound descriptor sets right now. I was thinking that there was 1 descriptor set per resource signature, but when I was doing some poking around trying to debug something earlier today, I saw that this one at least has 2. So shader bindings, not even sure if I was in here earlier, but looks a little bit different now. And this is our binding code that specifies what I'm going to call resource signatures descriptor sets, so don't be bugged by that. It's so hard-coded into my mind, but I will look into what that exact hierarchy looks like. But here you can see anywhere where we have a descriptor set bound to our shader, you can see what that, we have 3 of them right now. We have global resources, component level resources. So global would be anything that we bind the least frequently, and that's kind of a weasel word because with our bind list rendering approach, we actually bind all 3 of these with the same bind frequency. We bind them once per frame. But generally the idea is you want to group your descriptor sets by bind frequency. I think it's better. We decided to group ours by by functional relation. So that's a better way to say it. So the global resource signature right now has our textures, our texture buffer array, and our environment buffer, which is a uniform. So you can see we have a texture buffer type, we have a uniform buffer type. So right now in environment, I believe we just have the camera, a view proj of the camera pre-computed, and then we have a texture buffer array. Then components are really what I've been working on lately. So we have the object subsystem is renamed to mesh renderer buffer data because we're going to be expanding our concept of the object instance. Before, anything that got rendered more or less was in the object buffer, so we had a bunch of stuff in there we didn't need. We actually kept the material. We didn't have a material system before, so we kept all of our material parameters, of which we could only have 4, and they had to be uints, or at least 4 bytes inside of the object buffer struct. So that's no more. Now we have a separate material buffer, which is all Cal. He's been working on that for the last week or so, a couple weeks, which is fantastic. I'm incredibly excited about it. But anyway, mesh renderer buffer just has the model transform now, and actually I think now with Cal's work it also has index into material buffer, but no longer it has 1 layer of abstraction now, so it indexes into what material buffer you have in the material buffer array. And then these are what we're working on this stream. So spotlight buffer, we have an array of buffers for spotlights, an array of buffers for point lights, an array of buffers for directional lights. So now what we need to do, oh, I don't remember why I started talking about. Oh yeah, that was just something that we'd worked on since last stream, is just cleaning up this interface a little bit. So we now have the GPU side minus the shaders done. So we have buffers, they're getting bound to the GPU for spotlights, point lights, and directional lights, and now we just need to create the subsystems that will pull this, pull the data for the individual components out of the ECS and then into a span that we can just map right over. So let's get going. So for now, I'm just planning on creating a single subsystem for lights called the light subsystem, just to reduce code. Now, what I wanted to see, I'm going to go just very very simple for the first time, because eventually we're going to want to sort static, and all of the work that I had done on stream for sorting static due to a miscommunication, I then thought we didn't need, so I removed all of it, and then it turns out we kind of actually didn't need it, because Cal and I were meeting in the middle, because I was working on the object subsystem slash mesh renderer subsystem, as it's called now, and that was going to link up to the material subsystem, but he was working on that at the same time, so he ended up coming in and doing quite a bit of cleanup and adding quite a bit of just neat functionality into our build state. So it looks unrecognizable from when you've seen it last, but this is what we were working on last week on stream. So all this does is it pulls the mesh renderer and the transform out of the ECS, gets the material index now, which is what Cal did, then gets the transform, which is what I did, and throws it into a span, and then pipes that over to the GPU. So the question that I left off on earlier today was, so we need to get the point lights, the spotlights, and the directional lights components out of the ECS, and for each of those we need to get a transform. But I don't know if there's a better way. Cal wrote the ECS and it works really, really well, but I can often get caught up on doing things correctly because it's changed out from under me several times. But for now, what I'm going to do is just the direct approach of having an explicit ECS call for each of my 3 groups. So I need to get point light and transform. I need to get, I'll probably get feedback that there's a much nicer way to do this, but you gotta start somewhere. Okay, and we're going to need a light render state struct created. So let's see. First, what we want to do is forward declare. I think we want to, let's look at mesh renderer subsystem. Yeah. We're going to want to forward declare point light and spotlight and directional light and transform. And let's alphabetize those. And then we're going to want to include ECS forward. And that should be good for now. Oh, of course. I think these two are, this one is a class, these guys are structs, but let's struct, wow. Yep, okay. Now where did we put, oh, it's a separate class here. So now I need to create a light render state struct. So render state is the minimal subset of data that we need to pull out of the ECS to bind directly to our buffers. Kind of have your pragmas. Right, so we want, oh my gosh, what is this autocomplete magnificence? I can't believe it. Never happened before. Okay, so we want to have, let's look at material render state, or mesh render state. Yeah, we want, I don't think, so here's the question. Do I want to do any kind of caching system right now, or do I just want to blast them on through in the form of spans? And I think for now, let's just blast them on through in the form of spans, because we're going to want to, in phase 2, which may or may not happen this stream, we're going to want to treat static point lights, or static lights and dynamic lights differently. That will pave the way for both baked lighting, but also just, we're not going to have to map over the range of statics because they're not going to change unless add or remove, but that will require some caching. But for now, let's just blast them on through so we can regroup with Cal and figure out what exactly he's thinking there. So we want, let's see here. We're gonna need, what does point light look like? Where did I put point light data? Oh, it's in shader types, I think. Yeah, here it is. So we're gonna want a, oh, but now already we need the vector because we're gonna want to build these in place. But that's fine, we don't need it here. So for, let's just look at spotlight first. We're gonna want to pull the position out of the transform. And then the view projection we're going to want to calculate in the subsystem. And then the rest of it, with the exception of cast shadows, which I'm also not quite sure the best approach there. We can just directly pipe from the component. So let's grab a spotlight. I think I did point lights before. Let's be consistent. Oh, if we're going to have any kind of arbitrary sorting, we might as well do alphabetized. So earlier this week I just made these data objects. This will be what's actually present in the shader. So these are 16 byte aligned. And what the subsystem will do is go from the point light, or from the component, which has a lesser subset of this data. And just for the full picture, this is what the editor can hook into and allow you to edit. So then the subsystem is responsible for compositing the point light and the transform to build the final data that will pipe to the GPU. Let's just call them oh, that's what I wanted to do. So with the previous version of our renderer, we had a isInitialized variable here. And what we would do is we would wholesale map the entire buffer. So say if we had set a max size of 20 point lights, we would map, and we only had 3 of them that were actually in the scene. We would map 3 active ones and then 17 dummy data point lights. But the 3 active ones would have is initialized set to true in their internal data here. And the 17 dummies would be initialized with that set to false. So then in the shader, we would say for each point light in the vector of 20, if initialize is true, carry on with influencing lighting in the scene. And there's must simply be a better way to do it. And there is. I think this time around what we're going to do is, I don't know if it's going to be here or if it's going to be in the environment buffer struct, but we'll need to surface it to the GPU here. So uint32t point num active point lights. So now what we could do is we'll map this to the GPU, probably in our global environment buffer struct, and then we could just say on the shader side for I in num active point lights, and make sure that the active ones are in the front, which they will be because we'll just map the span to the buffer and make sure we put it in the front. Why don't you like that? Oh, you just haven't caught up yet. And maintain our order. I've really gone back and forth throughout my career with either struggling from imposter syndrome or feeling like I've totally got this in the bag. And professionally right now, I'm more in the totally got this in the bag camp. But there have definitely been times in my professional career where I've had imposter syndrome. But now with C++, I'm still more in the imposter syndrome camp. But what I use to prevent myself from falling prey to the black hole that is imposter syndrome is just the realization that it literally doesn't matter how much you know, because how much I know, because I will figure it out. And I love that. That is, so if anyone's ever feeling like you're not good enough to be here, or someone's going to find out that you don't know if calling std move on a vector invalidates the entire vector like last week, or if it just invalidates each item in the vector, just don't sweat it, because you will figure it out. And as long as you have the mindset that you will figure it out, then nothing will hold you back, and you will quickly catch up to where you need to be if you're not there already, which you probably are if you're thinking you're not. As I've gotten further and further into my career, I used to think I have to be perfect, but now I think, no, I have to set quality requirements and I have to meet those. And sure, those quality requirements have gotten higher and higher as I've gotten more and more comfortable in just programming in general, but if you have very specific rules as to what exactly you have to do, then it becomes, you don't have any more self-doubt or any insecurity or that void of anxiety, because what if I'm not good enough? Because you've already defined for yourself what good enough is. And that's the real power move. Okay, so we have our light render state, directional point spot. Now we have it here. I also don't remember if I had these headphones on last stream or if I was still complaining about my bitterly uncomfortable headphones, but the bitterly uncomfortable new headphones are now my work headphones because I'm generally on meetings less than I am listening to music or streaming here.